So we have 1150 grams over the molar mass of aluminum is 26.98 grams per mole. So 1150 divided by 26.98. So this is 42.624 moles for aluminum. So now we're going to use our mole ratio. So X is aluminum oxide, right? And then our mole value here is for aluminum. And the ratio here is 2 to 4. So X ends up being times 2 divided by 4, 21.312 moles of aluminum oxide. And then the last piece of this is we're going to solve for the mass of aluminum oxide by doing moles times the molar mass. The molar mass is 2 aluminum and 3 oxygen. So this becomes 21.312 moles times, so this is 2 times 26.98 plus 3 times 16, 101.96 grams per mole times 21.312. So this is 2172.97 grams. And then for sig figs, there is 3. So this ends up being 2170 grams. So this is how much aluminum oxide should have been produced. Now this is saying that 635 grams of aluminum oxide is obtained. So meaning that is what they got, 635. So up till now, everything we've done has been regular stoichiometry. So here's where the new part's going to come in. So we have actual yield over the theoretical yield times 100. So this is our 635 grams over 2170 grams. So we get here 635 divided by 2170. So we get here pretty much 29.3% yield. Okay, so when you are doing this, right, this is really the new piece. You need to have a stoichiometry number. So in this case, right, you'd have to calculate that first and then continue on. Okay, now keep in mind, this could have also been combined with limiting reactant. If I was given a mass here as well, let's say, I don't know, 50 grams, then I'd have to do exactly the same thing, but I'd have to make that choice of which one is limiting in between. And that's really kind of the maximum where this is going to go. So the biggest, I guess, most complex problem you'll see involves stoichiometry, limiting reactant, and then at the very end, you have percent yield. Okay, so give this next one a try. Iron 3 oxide reacts with carbon monoxide to produce carbon dioxide and iron. If 300 grams of iron is produced, right? So this is saying that this is produced when 425 grams of iron ore is used. So iron ore is another term for iron 3 oxide. Okay, what is the percent yield? So pause the video, give this a try, have your periodic table nearby, and let's see how you do. Okay, so let's do this. So we have here Fe2O3 plus carbon monoxide, which is a gas. Here we have carbon dioxide and iron. Okay, so we'll need a 2 for the Fe. Fe2, we have 2 here. So we have 4 and 2. But that's not going to work because we don't want to touch this, so there's 2 there. Okay, let's see. If we put a 3, so sometimes you need to do kind of trial and error here to see what you get. So here this will give us 6 oxygens. So if we put a 3 here, we get 3 plus another 3. We'll still have 6 oxygens and now 3 carbons. Okay, here we go. So we have the mass here of being 425 grams. And we want to know the mass of the iron that's produced because we want to compare it to the 300 grams of iron that was made in the real reaction. So this is our actual yield. So the first thing we're going to have to do is we have to, I don't know why that's there. Anyway, so we have to find the moles of iron 3 oxide first by doing mass over the molar mass. The molar mass is going to be 2 iron plus 3 oxygens. So let me get my periodic table here. Okay, so we have 55.84 times 2 plus 3 times 16. So we have the molar mass here of, so we're going to have 425 grams over 159.68 grams per mole. So 425 divided by that, we get 2.6616 moles, and that's for iron oxide. Okay, so we want to solve for iron. Our moles of iron oxide are going to be on the denominator. And then our coefficients here are going to be 2 and 1. So our X value is going to be essentially our moles times 2, which is going to be 5.323 moles, and that is for iron. Lastly, let's solve for our theoretical, which is moles times molar mass. This is just going to be 1 iron here. So that's going to be 5.323 moles times 55.84 grams per mole. Okay, so we get 297.24 grams. And actually for sig figs, it's just 1, so this rounds to 300. So this is actually, funny enough, so percent yield, you take your actual yield and you divide it by your theoretical yield times 100. So in this case, it happens to be 300 over 300, which is 100%. Okay. Now, in real life, when you're doing this, this might be the only example you'll ever see 100%, but of course, this is just an example to show the procedure of going about doing this, right? So we have 100% yield here. Okay, so the steps are balanced chemical equation. You need to solve for your theoretical yield first. Very rarely are you given the theoretical yield. That was like the sugar example. Remember when we did this sugar one? So this would be like worth 1 mark, okay? You're literally just plugging in the numbers. When you're doing stoichiometry and you're involving the calculation of theoretical yield, right, becomes a more meatier question because you now have to do multiple things. So something like this with the stoichiometry involved would probably be worth maybe 5 or 6 marks. If you had to find limiting reactant on top of that, probably 6 or 7 marks, right? So it kind of depends on how much you have to do or how much information you're actually given. Okay, and that's the end of this unit. So we're going to take this concept. Don't worry, stoichiometry is not going away. You will see this concept in the last 2 units of this course. Maybe with a different twist on it, but still using very much so the same procedure.